Welcome back, everybody. Learning's a hobby here. I want to go over the last section in Chapter 4 in Tao's Analysis 1 book, which is what we're going to do in this section. So let's do it. Let's jump right into it. It's kind of a short section, so this video is probably going to end up being like 5 minutes long, but let's go through it anyway. So here I'll bring up my summary. Just move some things out of the way on my screen. Okay. All right, so we start here with proposition 4.4.1, which is, oops, what is this doing? Let me see if sorry, just bear with me. Let me just make the screen a little bit bigger. Okay, interspersing of the integers by rationals. Let x be a rational number, then there exists an integer n such that n is less than or equal to x is less than n plus 1. In fact, this integer is unique. For example, for each x, there's only one n for which n is less than or equal to x is less than n plus 1. In particular, there exists a natural number n such that n is greater than x. There's no such thing as what that says is there's no such thing as a rational number which is larger than all rational numbers. The proof of this he leaves to the exercise set, so we'll see that in the next video. We'll do that as the first exercise in the exercise set. And then in red here, I just have my this note is not in the book, it's just my note, but this proposition here implies that the rationals have the Archimedean property. So that'll be useful in one of the propositions that we'll prove in this section in a few minutes. Okay, remark 4.4.2. He says, Tao says the integer n for which n less than or equal to x less than n plus 1 is sometimes referred to as the integer part of x and is denoted by that symbol that I have written there. Or sometimes you'll hear it referred to as the floor of the number x, or the greatest integer of x that's less than or equal to x, and so on. So I don't remember. I think we have used this symbol before in Spivak, actually, now that I'm thinking about it. So maybe you guys remember that from Spivak. But anyway, that's what that symbol means. Proposition 4.4.3, interspersing of rationals by rationals. If x and y are two rationals such that x is less than y, then there exists a third rational z such that x is less than z less than y. Or sometimes this is sort of like a density proposition. So the rationals are dense. Here's the proof. Let x, y be rational numbers such that x is less than y. Then 1/2 x is less than 1/2 y because 1/2 is a positive rational. And remember that multiplying rationals by positive rationals preserves order. And that implies x is 1/2 x plus 1/2 x, which is less than 1/2 x plus 1/2 y, which is less than 1/2 y plus 1/2 y, which is equal to y. Therefore, z equals 1/2 x plus 1/2 x, which you can write more simply as x plus y over 2 is rational, and it's a rational number between x and y. All right, proposition 4.4.4, there does not exist any rational number x for which x squared equals 2. We've actually already proved this, maybe more than once even. We proved it, I think, we definitely proved it in Spivak, but then I think we definitely proved it also when I went over Stillwell's, we did chapter 1 in Stillwell's History of Mathematics textbook. If you may or may not know, but if you look in the playlists, I did chapter 1 in that book, and we talked about square root of 2 and so on in there as well. But we'll do it again here as well, because in this in Tao's book, he does it with a descent proof. So it'd be interesting just to show you that. So, but there are parts of it that he leaves for the exercise set. So rather than, do it piecemeal, excuse me, do it piecemeal here, I'll just do the whole thing in the exercise set. When we get to the exercise set, which is this will be question 4.4.3. Okay, proposition 4.4.5. For every rational number epsilon greater than 0, there exists a non-negative rational number x, such that x squared less than 2 less than x plus epsilon squared. And this is sort of like the big theorem in this section. So here's the proof. It requires a couple of lemmas to be proven, which Tao asks why in the proof. So I'm actually reproducing Tao's proof here with all the details filled in. I don't think, actually, let me just check real quick. I don't think he asks you to prove those things in the exercise set. Let me just double check. Yeah, he doesn't. So anyway, that's why I'm doing it here, because he doesn't ask you to fill in the details in the exercise set for some reason. So might as well do it here. All right, so here we go. So we'll do this by a proof by contradiction. Assume there's an epsilon in the rationals such that epsilon greater than 0, and for every x in the rationals, x is greater than or equal to 0, x squared greater than 2, or x plus epsilon squared less than 2. In other words, I'm assuming the negation of the proposition because we're going to do this by contradiction. All right, then here I have star in front of this because we're going to use this as a hypothesis in what I'm writing as lemma 1 down below. Then for any 0 less than or equal x, such that x squared less than 2 implies x plus epsilon squared less than 2. Right? In other words, if the first part of the disjunction here is false, then the second part has to be true, right? Okay, also I should make as a note here, we don't have to worry about x squared being equal to 2 or x plus epsilon squared being equal to 2 by the previous proposition, the fact that square root 2 is not rational. So we only have to worry about strict inequalities here. All right, so I have to prove a lemma here, which Tao doesn't do in the proof. He says you should do it, so that's why I'm doing this here. So let n be a natural number. Then if star is true, so if that statement that I wrote up above next to the star is true, then n epsilon squared is less than 2. So we'll do this by induction because n is a natural number. So base step, n equals 0. Obviously, 0 squared is less than 2 because 0 squared is 0, which implies that 0 plus epsilon squared, which is equal to epsilon squared, is less than 2. So that proves the base step. And then the inductive step, assume n epsilon squared less than 2 for some natural number n. Then n epsilon plus epsilon squared equals n plus 1 epsilon squared is less than 2 by star. Therefore, the proposition holds. So if x is a non-negative rational number such that x squared is less than 2, then x plus epsilon squared also has to be less than 2. That's what we just proved. Right, then there's another statement that he asks us to prove in the proof, so I'm doing that here. I'm just labeling it as lemma 2. Let n be a natural number and epsilon be rational such that epsilon is greater than 0, then n epsilon is greater than 0. And the proof is just by proposition 4.2.9 part E, right? The product of two positive rational numbers preserves order. So that proves that statement. And then here, finally, we can get to the contradiction that we want. By proposition 4.4.1, there's a natural number n such that n is greater than 2 over epsilon. This is why I wrote that note up above. The proposition 4.4.1 implies that the rationals are an Archimedean field. That implies that n epsilon is greater than 2, which implies that n epsilon squared is greater than 4, which obviously 4 is greater than 2. This contradicts lemma 1, therefore the original proposition holds. Right, so that we've proven then that this statement here is true for every rational number epsilon that's greater than 0. There exists a non-negative rational number x such that x squared less than 2 less than x plus epsilon squared. What that is telling us is that well, he says it in a note down here, but where does he say it? Proposition 4.4.6, the one we just talked about, indicates that while square root 2 is not rational, we can get as close as we wish to square root of 2 by taking a sequence of rational numbers whose squares get closer and closer to 2. There's also an example that he has here. So before I read the final paragraph here, let me just go through the example. So just an illustration of what we were doing up above. If star, sorry, the star here refers not to the lemma up above. Maybe I should have used a different notation here, like double star or something. Maybe I'll do that so it's not so it's not confusing. It's my I don't know. I'll do it afterward. My pen doesn't seem to want to cooperate with me right now. So if epsilon equals 0.001, we can take x equal to 1.414, since x squared equals 1.999396, which you could check, and x plus epsilon squared is 2.002225. What you can think of this intuitively as just thinking about whatever epsilon is, as long as it's positive. If you take x closer to the square root of 2, then square root of 2 minus a distance of less than square root of 2 minus epsilon, then that number will the number itself will square less than 2, and if you add epsilon to it, it'll square to a number that's bigger than 2. So here he's just doing an example of that. Okay, he says also here to note, we will use the decimal system for defining terminating decimals. That's what, in the example, that's what we did. So we don't really have to define new things for that, because you could write each of these as fractions, right? You can write them as rational numbers. Okay, and then finally, so by what I read out before, square root of 2 is not rational, but we can approximate square root 2 in the rationals by taking a sequence of rationals that get closer and closer to the square root of 2. This seems to imply that we can create a square root of 2 by taking a limit of such a sequence, right? For example, 1.4, 1.41, 1.414, et cetera, et cetera. If you notice those numbers, when you take their squares, the squares get closer and closer to 2. And this is the idea behind how we're going to actually construct the real numbers in the next chapter in Tao's book. So that's, the idea behind the Cauchy sequence method for constructing the real numbers. He also says here there's another method called Dedekind cuts that we'll not explore in Tao's book, but we will explore it in Spivak's book. So we will see both methods. And then finally, one can also proceed using infinite decimal expansions, but there's some technical issues that make this method more complicated than other approaches. But he says see Appendix B. So we'll do Appendix B too, because he talks about the decimal construction of the real numbers in Appendix B. So we'll do that later on, because I don't want to do that one right now, because it involves series and things like that. So maybe we'll take a look at Appendix B after we talk about infinite series in either Spivak or in Tao's book. So that's the end of this my summary for this section. Let me stop the screen share. So we only have one last little bit of things to finish up here in chapter 4, which is the exercise set for this section. I think there's only 3 questions, so I should be done with that. I haven't started on it yet, but I should be done with that maybe tomorrow. So once I finish that and post the video, then we'll finally be up to chapter 5, and we'll get to the construction of the real numbers, first by the Cauchy sequence construction, and then after we do that, we'll go back to Spivak's book, go to his epilogue, and construct the real numbers using Dedekind cuts. So we'll be able to see both of those methods. And then finally, after that, we'll go back to start on derivatives and integration in Spivak's book, and we'll continue from there. I'll talk more about this in my August vlog. I don't want to get too off topic here in this one. So that's the end anyway for my summary here. Thanks for watching, everybody. I'll see you in the next video, and keep learning until